Okay, so let's get started. We're going to be taking a look at working with our alpha N tuning once again with our Link G5 and G4X systems, where now we're going to be looking specifically at working with alpha N in a force induction application. We'll find that this is a little bit of a unique situation, but I want to have a separate tutorial on this topic because it might be something that you run into when you're trying to program with your Link. Now let's talk about this specific situation. This would be for the best example would be a Nissan RB26 engine. They're fitted with individual throttle bodies and a common plenum so that you're able to push positive manifold pressure into the engine. You'll find at idle and part throttle, they're problematic to calibrate and map with a standard map pressure reading. So we can't use in our main field table here, for example, MGP for the input. We have to calibrate and tune things with throttle position for an RB26 engine. Now the problem's going to be, as we change our throttle angle, we know the boost is going to increase, or we're going to be in vacuum, so idle, part throttle, get into full throttle, you'll have a certain amount of boost. If we have a different boost pressure target, let's say we're going from 10-pound target to 20-pound target, and we're at 100% throttle, we're going to be in trouble because the Link isn't going to be able to calculate the new amount of fuel it needs to add in order to compensate for a couple more pounds of boost. So we have to go about this in a very specific manner. Now you may also be in a situation where you have a really radical camshaft or camshafts installed into your engine and you pull little to no engine vacuum. You're going to find that you really can't calibrate and map things out based on MGP as your load input to your fuel table because you'll have very little resolution to be able to track what's going on with the engine's vacuum. Now once you get into full throttle and you get into boost, that situation won't be so bad because as you get up into positive manifold pressure, the MGP will track properly in that higher load situation. But it's the vacuum and idle that can be problematic. So in either situation, we are going to want to tune in an alpha N strategy, but we're in this particular situation where throttle position as the load input at the table, 80 to 100% throttle here, isn't going to be able to characterize moving boost. So if we have multiple boost targets, this is not going to be a reliable way for our fueling delivery for our engine or calculation for our engine. It's simply not going to be able to keep up with what's going on with varying boost levels and airflow as it's coming into the engine. How do we get around this? It's actually pretty straightforward. Let's go in here from our field table. Let's go into our basics area. In our basics area, we have, whether we're in our fuel equation mode, modeled or traditional, we can do the alpha N tuning either way. Let's assume we're in our model mode here. We have our equation load source set currently to load equals map. This is normally what you'll always calibrate and tune pretty much any engine with the Link using this specific option. What this is saying is that if we double our map pressure, we double our injector pulse width. That's going to have that linear type of relationship. When we're in an alpha N strategy, we don't have a reliable map pressure reading from one situation or another. So you may find individual throttle bodies, you give it some throttle input, your TPS to map sensor relationship isn't linear, so we'll find that we can't properly calibrate things. Or again, you may be in a situation with a radical camshaft installed into the engine. In that situation, you may have very good resolution in vacuum. We can't use the load equals map as our equation load source. We'd want to switch it over to load equals baro. That's going to be what we traditionally always use for a naturally aspirated engine getting mapped with an alpha N strategy. But the problem is going to be if we're getting into boost, we want to be able to have that relationship that if we double our map pressure, the injector pulse width doubles. We still want that type of relationship, but when we're in vacuum, we want to rely on look at the baro pressure reading so that it's going to be a more reliable tracking for our fueling calculation. That's where we have our third option here that's going to be for this specific situation, load equals baro divided by map crossover. What this is going to do is use the baro pressure for idle part throttle up to atmospheric pressure, and then it will switch over to looking at your map pressure reading and then tracking that map pressure as you're getting into positive manifold pressure, into boost, and then we'll double your injector pulse width as the map pressure doubles. So it's going to have that ideal relationship that we want to have in positive manifold pressure, but in vacuum, it'll act like a normal naturally aspirated engine in terms of the tracking for your load for baro pressure. So we're going to go ahead and choose this option. Now, when we do this, a couple things to consider for setting up our file. So we have it set on model, again, model or traditional, we'd set it the same, so load equals barrow over map crossover. If we jump in here to our table, we configured this in a very specific situation. We went from 0 to 100% throttle, moving in these very...
Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.